right, this is lecture 21 on section 5.5 on L'Hopital's rule. So the first thing I want to do is I want to bring us all the way back to limits from the beginning of the semester. And if we revisit some of these limits that we've seen before, we'll notice that start to bring some of these things back. So if we look at the limit as x goes to 0 of sine x over x, this was a special limit. When you plug in 0, you get 0 over 0, but we know that the answer here is supposed to be 1. For number 2, when you plug in infinity on this one, you get infinity over infinity. But we know that we had rules that said, oh, when the higher degree is in the numerator, this goes to infinity. So this should be infinity. This one I told you should be 1, but if you plug in, you get 0 over 0. And this one, we don't have any strategies when we have a natural log. We know that this is supposed to be infinity over infinity. So how can we find a better way using calculus, using derivatives, to find these limits? Well, we end up with something called L'Hopital's rule. By the way, the S is silent there. Some spellings leave the S off, but I was taught that the S stays. So when you have a limit that is a fraction, and that's an indeterminate form of type 0 over 0 or infinity over infinity, then we can use L'Hopital's rule to take the limit as x goes to a of the derivative of the top divided by the derivative of the bottom. Now, I want to caution you here because keep in mind, this is not replacing the quotient rule. So if you are taking the derivative of a fraction, you still have to take the derivative of a fraction using the quotient rule. However, if you're taking a limit of a fraction, you can use derivatives to help you take that limit. Now, a quick note about why it works. If you think about looking at the limit as x goes to a of n of x over d of x. Now, let's suppose that it's type 0 over 0. If it's type 0 over 0, that means that when you plug in the a, both pieces, n of a and d of a, are both 0. That's going to be a factor we're going to use. So essentially, if what we do here is use the linear approximation of each of these, that's going to be n prime at a times x minus a plus n at a. And for the bottom, it's d prime of a, x minus a plus d of a. But now we know that the n of a and d of a are 0. So these last two terms go away. And we're left with the limit as x goes to a of n prime of a, x minus a, over d prime of a, x minus a. And then your x minus a's cancel. So you're left really with the limit as x goes to a of n prime at a over d prime at a. So essentially, if you take the derivative of the top of the bottom and you plug in your a, that's equivalent to your original limit. Okay, so it comes from, you can see that it kind of makes sense when you look at the linear approximations. Okay, now keep in mind there are two other types of indeterminate forms that we could come across, and that's something that's 0 times infinity or something that's infinity minus infinity. There are also some indeterminate forms that involve exponents, but we're not going to get there. Key thing with those two types of indeterminate forms is that you're going to have to turn it into a fraction to be able to use L'Hopital's rule. So let's see how this plays out. So we know that these examples from up above were all either 0 over 0 or infinity over infinity. So that means that I'm eligible for L'Hopital's rule. I like to write a little L apostrophe H or above my equal sign when I use it so that you know that I didn't just do some kind of weird algebra. So this is the limit as x goes to 0. And the derivative of sine is cosine. Derivative of x is 1. And when you plug in 0 to cosine, you get 1. Which is exactly what we had before. Number 2, this one's infinity over infinity, so we're allowed to use L'Hopital's rule. Limit as x goes to infinity. Derivative of the top is 3x squared plus 1. Derivative of the bottom is 2x. Now, go ahead and evaluate your limit. So when you plug in infinity, you again get infinity over infinity. Now, there was nothing in the rules that said we couldn't use L'Hopital's more than once. So at this point, this new limit satisfies the criteria that it has the form infinity over infinity. So I can use L'Hopital's rule again. As many times as I need, actually. So this becomes 6x over 2. And when you plug in your infinity, now you get infinity over 2, which is infinity, right? Which is what we said the answer should be. So some quick and easy ways to get our derivative, to get our limits here. Now this one, I didn't have a way to prove this to you. We said this should end up being 1 because this is the way they define e. E is the number such that this limit equals 1. But it's typing 0 over 0, so we can go ahead and use L'Hopital's rule. And we get e to the x over 1. When you plug in 0, you get 1 over 1, which is 1. And then number 4, when you take your derivative here, this is, when you plug in infinity, it's infinity over infinity. So it's eligible for L'Hopital's rule. And we're going to end up with 1 over x all over 1. And when you plug in infinity, that's 1 over infinity, which is 0. So we can get our answer that way. Okay, so it's kind of nice when it's already set up as a fraction.